So in continuation with the previous session, we have started discussion on optimal binary search trees using a dynamic program. So the challenge here is that for a given set of keys, many binary search trees can be generated, but the objective is to generate optimal BST using dynamic programming. So in continuation with the previous session, let us assume that the keys given are A1, A2, A3, and so on up to AN, for which an optimal BST must be generated. And the optimal BST is the BST that gives an optimum cost of the tree. And how do we calculate the cost of a binary search tree? We do so by calculating how many number of comparisons will be required for searching a key. There might be many keys in the binary search tree, starting from A1, A2, A3, and so on up to AN. There will be n number of keys in the BST. So searching for each key, how many number of comparisons will be required? That will be the cost of searching for a single key. And the cost of the tree itself will be the average cost of searching for the keys. So that will be what is the cost for searching key 1, what is the cost for searching A2, what is the cost for searching A3, and so on up to the cost for searching the key AN. You are going to find out the cost for searching each key value in the BST. Then you are going to take the average. That average will give you the cost of the BST. And as such, for a given n number of keys, you will be able to construct many number of BSTs, and the BST that has minimum cost, that will be called as an optimal BST. Now, as I'm saying, searching for a single key. And whenever you search for a key, there will be two cases. It may be a successful search or it may be an unsuccessful search. If you are searching for some key AI, where I is between 1 and n, that is, you are searching for any key. Maybe you are searching for A1, A2, A3, or so on up to AN. If among these n number of keys, you are searching for any key AI, which is available in the tree, then you'll be able to find the key, then that will be a successful search. And let the probability of the successful search be represented by P of I. P of I is the probability of a successful search for the key AI, where AI is available in the binary search tree. If you are searching for some key X, which is not available in the BST, then it will be an unsuccessful search. And let QI be the probability of the unsuccessful search, where you are searching for some key X, which is not available in the tree. That means this X is said to belong to EI. X belongs to EI. What is EI? In the previous session, I told that EI is an ith equivalence class. Ith equivalence class. And this equivalence class will have a set of keys which represent an unsuccessful search. So here, you are searching for some key X from some equivalence class, that is, which is an key that is not available in the tree. Then it will lead to an unsuccessful search. And let the probability of unsuccessful search be Q represented with Q of I. Now, whenever I'm talking about probabilities P of I, Q of I, then the sum of all these probabilities should be equal to 1. That is a general logic we use in representing probability of different cases. The sum of all successful searches plus the sum of all unsuccessful searches should be equal to 1. The sum of all the probabilities should be equal to 1. Now, let us try to find out what is the method for calculating the cost of a binary search tree. Assume that there are some keys 10, 20, 30. I have already constructed a BST. There is a BST that is already available. I want to find out its cost. How do I calculate the cost? So assume that these are the keys 10, 20, and 30. Then P of I represents the probability of a successful search. Again, there are 3 values given here, 0.5, 0.1, 0.05. 0.5 indicates the probability of 10. 0.5 is the probability of a successful search for 10. 0.1 indicates the probability for searching 20. 0.05 is the probability for searching the key 30. So these are the probabilities of the keys that represent the successful search. Then, apart from the keys 10, 20, 30, which are available in the tree, user may be searching for some other keys other than 10, 20, 30. So I might be searching values which are less than 10, which leads to an unsuccessful search. And what is the probability of an unsuccessful search where the user is trying to search for less than 9? So 0.15. This is the probability of the user searching for values which are less than or equal to 9. That is less than 10. Less than 10. 0.05 is the probability of an unsuccessful search where the user searches for values greater than 30. It is nothing but this is the probability of E naught. Here is the E naught in the tree. E naught is an set of keys. It's an equivalence class representing a set of keys, not a single key, but a set of keys. What are those set of keys? Any key which is less than 10 belongs to E naught. And whenever user is searching for some value which is less than 10, then the searching stops at E naught. And whenever search stops at E naught, which is a leaf node, that means the search is unsuccessful. Now, what is the probability that user searches for some values less than 10? The probability is 0.15. The probability is 0.15. 0.15 is the probability where the user searches for any value less than 10. In the same way, this is the probability for the set of keys in E1, probability for set of keys in E2, and finally 0.05 is representing the probability of searching the keys in E3. So you have keys, you have probabilities of successful searches, and you have probabilities of unsuccessful searches. Right? Now, how do I find the cost of this tree? So the cost of this tree can be calculated by using this formula. The first term here is the probability of successful searches. The second term in the equation is the probability of unsuccessful searches. And the sum of successful searches plus unsuccessful searches. This is what is going to be the total cost of the BST. Now, if I start with finding out the first term, which is the total probability of all the successful searches, which is equal to the sum of product of probability into its level. The sum of probability of the key into its level, and all the keys you are going to sum up. It's the sum of products of the probability multiplied with the level of the key. So for that, this will be the formula. If I expand, this will be the formula. For each key 10, for the key 10, you have to multiply its probability and its level. So the probability of 10 into the level of 10. What is the probability of 10? 0.5. So this is the probability of 10. Now, what is the level of 10? Level is within the tree, within the given tree, what is the level at which 10 is present? So you can see here, this is level 1, this is level 2, and this is level 3. Now, what is the level of 10? The level of 10 is 2. So that is, what is the level of 10? The level of 10 is 2. So for the key, the probability of 10 into level of 10. In the same way, for the next key 20, its probability into its level plus third key, its probability 30, P of 30 into level of 30. And sum of all this, there are 3 keys, 10, 20, 30. For each key, find out the product of its probability and its level. Add all these things. That will be the probability of all the successful searches, which is 1.2. In the same way, calculate the probability of unsuccessful searches, which is, I'm calculating this part in the equation, which is equal to the probability of all unsuccessful searches. Now from the tree, what are all the unsuccessful searches? E0, E1, E2, and E3. These are the leaf nodes that represent unsuccessful searches. Now for E0, for this set of keys, E0, its probability into its level minus 1. Probability of E0 into level of E0 minus 1. So what is the probability of E0? 0.15. So the probability of E0 is 0.15. Then what is the level of E0? Level of E0 is 3. Assuming that the levels start from 1, here it is level 1, this is level 2, this is level 3 in the tree. The level of E0 is 3. So 3 minus 1 is 2. So this is how I got this 2. Now, in the same way, I am going to calculate for E1, what is the probability of E1? And what is the level of E1? Minus 1. And so on. There are 4 leaf nodes, E0, E1, E2, and E3, which represent the unsuccessful searches. So for each unsuccessful search, what is its probability into what is its level? Minus 1. And now this you'll calculate as 3.4, which represents the probability of unsuccessful searches. So what is the total cost of the binary search tree? It is equal to the probability of successful searches plus unsuccessful searches, which is 4.6. Now, once a BST is already there, this is the process through which you are going to calculate the cost of a BST. Right? Now, the challenge is that you have to construct the BST itself such that the cost of the BST is minimum. Such a BST you have to construct by using dynamic programming. And this is the process through which you can construct optimal binary search trees using DP. The criteria is like this. This criteria is generic for all the problems of dynamic programming. So if you want to use dynamic programming for solving a problem, then this problem must be a solution which is the result of a sequence of decisions. So this given problem of constructing an optimal BST should be solved by taking a sequence of decisions. Then the second criteria for using DP. A bigger problem will be divided into number of subproblems, and each subproblem must hold the principle of optimality. The main problem should hold the principle of optimality, and each subproblems must also hold the principle of optimality. Now, these two rules must be applicable for any given problem if you want to solve it by using dynamic programming. This is very much common for all the DP problems. Now, in particular to constructing an optimal BST, we are going to make a sequence of decisions. That means we are going to solve the problem in a number of steps. One decision will be taken in each step. So at each step of constructing an optimal BST, a decision is made. What kind of decision we want to make? We want to make a decision regarding which key among the available keys, which key must be selected next to insert into the tree. A decision needs to be made among all the available keys, which key must be selected for making it as the root. For example, I have some keys, a set of keys that are available, which are A1, A2, A3, and so on up to AN. These are the available keys, A1 to AN. Now, among all these available keys, which one of them should I select as the root of the tree? That's the first decision I'm going to make. Which one of them should be made the root of the tree or a subtree? Which one of them should be made the root of the subtree? Assume that I have, among all these keys that are available, I have made a decision and I have selected AK. This AK, I have decided that it will become the root of the tree. It will be the root of the tree. Okay, now if I have decided AK is the root of the tree, so this is how your tree looks like. AK, this is the key I have made as the root. Then if AK is the root, then all the keys which are less than AK will get into the left subtree, and all the keys greater than AK will get into the right subtree. This is the property of the BST. If the parent is AK all the values less than AK will be in the left subtree. All the values greater than AK will be on the right subtree. This is the property of the BST itself. So if at some point of time, I have made a decision that AK is selected to be the root, then all the values less than AK will get into the left subtree. What are all the values that are less than AK? Less than AK are A1 to AK minus 1. A1 to AK minus 1. These are all the values that will be less than AK. What are all the values greater than AK? AK plus 1 to AN. It's nothing but these are the set of keys that are there, and in between there is AK. In between there is AK. Then these are all the values that are less than AK. And AK will be the root. Then all these values will be the values greater than AK. The A1, these are all the values which are less than AK. Now, how can I represent all the values less than AK? It will be A1 to AK minus 1. How can I represent all the values greater than AK? It is AK plus 1 to AN. These are all the values that are greater than AK. Right? So that is what I have written here. Left side tree, left subtree, which will contain all the values A1 to AK minus 1. This is the right subtree R, which contains the values AK plus 1 to AN. Along with the internal nodes, also there will be dummy leaf nodes, E0, E1, E2, and so on. In the same way, leaf nodes, left subtree, and which leaf nodes will be there in the left subtree? Those are E0 to EK minus 1. And which leaf nodes will get into the right subtree? EK to EN. Right? So this is how in each step you are going to select one key and you make it as the root of the tree. Then you'll be separating all the remaining values into left subtree and right subtree. And you are going to repeat this process for n number of steps. So these are the formulas now. I have decided AK will be the root. Then immediately all the remaining values will be divided into two halves, the left subtree and the right subtree. Now, how do I calculate the cost of the left subtree? And how do I calculate the cost of the right subtree? And these are the formulae. The same formula as I have discussed, but left subtree contains only values from 1 to k minus 1. So this summation of values only is going to change. Remaining formula will be entirely same, only what are all the internal nodes? The internal nodes are from A1 to k minus 1. So that part only will change. Then how do I calculate the cost of the right subtree? It contains nodes from AK plus 1 to AN and the leaf nodes from K to N. So this will be the formula. Internal nodes are from K plus 1 to N. Leaf nodes are from K to N. And this is the probability of successful searches plus the probability of unsuccessful searches. Now, if I know, already I know what is the cost of the left subtree and what is the cost of the right subtree. Separately, I know this. I know what is the cost of left subtree. I know what is the cost of the right subtree. Then how do I calculate the cost of this entire tree? This is the formula. The probability of K, the probability of the AK plus the cost of the left subtree plus the cost of the right subtree plus the weights from 0 to n. the weights from 0 to n. And how to calculate these weights? How to calculate the costs? How to calculate the cost of the entire tree? I'll be discussing in detail in the next session, where I'll also solve an example problem using this generic formula. This is the generic formula for calculating the cost of a tree, where the tree contains nodes from I to j. The tree contains the nodes from I to j. And this is a recursive formula. You can see that C of ij, C of ij is calling C of ik minus 1. It is also calling C of kj. That means a function C is calling itself. So this is a recursive formula which represents the use of dynamic programming for solving the BST problem. So how to use this formula, how to apply this formula, and how we will be able to generate an optimal BST. Let us learn that in the next session, where I'll solve an example problem using this formula.